Okay, so just repeat it here. So from now on, you should be able to remember the idea here. When you're looking at the projection, particularly when you're looking at the length of a projection, so how would you do that? You can simply use the A dot, the direction that you are projecting. That'll give you the length of the projection. Okay, so A vector dot B hat give you the length of projection. Okay, yeah. This conclusion is very useful. You probably will use that quite a bit in terms of getting the length of a certain projection. Any questions here for this point? Okay, good. Okay, so in previous lecture, at the end of the lecture, we were looking at the volume of a parallelogram. Okay, so I'll just quickly, because I need that conclusion here. Okay, so the volume of this parallelogram. So looking at the volume of parallelogram, we derived, using cross product and dot product, in the end, what we end up with is this. So we said the volume, equal A dot B cross C. Okay, so the volume equal A dot B cross C. Okay. And more precisely, it should be absolute value of this, because it could give you a negative value. The volume is positive. So, but anyway, so for brevity, let's leave it as this is. Okay. So that's where we find the volume of this parallelogram in the previous lecture. So we're going to make use of this conclusion into this. Okay. But before we move on here, let me ask you a simple question though. Okay. So this is the volume of a parallelogram, and I'm gonna maybe construct another simple geometry here using 3 vectors. So same orientation as previous one. So you have A, B, C, like this one here. So instead of constructing a parallelogram, so let's construct this so-called tetrahedron. So basically, the geometry. Basically, instead of construct parallelogram at the bottom here, construct a triangle at the bottom, and then connect all the vertices. Okay, that's what we call a tetrahedron. Okay, so now the question here is, what is the volume of this tetrahedron? So we derive the volume of this parallelogram, right? So what would be the volume, given if let's say ABC same as this ABC here, what's the volume of this guy? You can take a guess before even do any derivations here. What would be your guess? 1/2? 1/3? Yeah, 1/3 is a very common guess.
1/4?
1/4? No. 1/3 is not right, 1/4 is not right. It's going to be, well, let's see how it's going to be, right? Okay. So we'll do the very similar approaches, okay, as deriving that one there. So, tetrahedron is a triangle here, so at the bottom, so just like the parallelogram, but this time it's triangle, which is 1/3 base area times height. Right. Okay. Previously it's just base area times height. So this time it's 1/3 times base area times height. Well, what's the difference for if the orientation of this one is the same thing? I guess the height will be the same thing, right? But the base area here, this is the parallelogram, this is what? Triangle. So this triangle is actually going to be how much is this? compared to this 1/2, right? It's going to be 1/2 of this base area here. So 1/2 of the base area. Base area, we also did an exercise for parallelogram. The base area using vector concept is 1/2 the magnitude b cross c, right? B cross c. Okay. Yeah. And the height is a vector dot the direction, perpendicular direction to the plane formed by B and C, right? As we just. So basically, this is the height. We're looking for height. We're looking for the height. We're not looking for a vector. We're looking basically the length of a projection. Projection of A in which direction? In the direction of n hat. And n hat is perpendicular to the plane formed by B and C at the bottom here, right? So as we emphasize here, how do I find the length of a projection? The vector dot the direction, okay? Or the unit vector. So that's why this is where this is from. And n hat, we know that n hat is what? N hat is perpendicular to B and C. So that has to be a B cross C and divided by its length. So that has to be normalized, right? So if you substitute everything into it, you'll see that it's 1/6, okay? And A dot B, okay, cross C. So 1/6. The volume of a tetrahedron is 1/6 of the volume of this parallelogram. Okay? Yeah. Just on the front side here. Any questions? All good? Okay. So yeah.
Where did n hat come from?
N hat at here represent is the unit vector or the direction perpendicular to the plane formed by B and C vector here. So we're looking for the height, right?
Yeah.
And height is basically you project A into the direction.
Yeah.
This is the height, right? Yeah. That's right. Okay? That's why we use the dot part, right? Yeah. So okay? Yeah. So again, I want you to memorize this thing here, okay? And also understand, if you're looking for the length of a certain projection of one vector into another direction, the simplest concept is this vector dot that direction. That direction is a unit vector, okay? When we say direction, we always talking about the unit vector there. Okay? So now let's go into a more interesting topic. So first, we're going to look at the equation, okay, of planes, okay, in 3D space. Okay, so, and then we'll look at the equation of lines in 3D space. Okay, so let's model this question slightly a different way here, and so we can facilitate us deriving this equation plane. We're talking about equation of plane, so I think from your high school geometry, everybody knows that, okay, 3 points determines a plane, right, uniquely. Okay, so 3 points at the different locations will determine the plane. So let's say we call this as P1, P2, this is P3, and this is P2 at here, right? Yeah. So 3 points determine plane. And I can draw a plane, okay, basically passing through the 3 points at here. Okay? Yeah. So the question here is, given the 3 points P1, P2, P3, what will be the plane equation, right? That's 3 points. So let's just say the coordinates of the 3 points x1, y1, z1, x2, y2, y2, z2, and x3, y3, z3. Remember, I use bracket, small bracket for coordinates. Right? Okay. Okay. So now, what I'm going to do is, I got the 3 points given, and then I can construct, okay, 2 vectors out of the 3 points at here. Okay, you construct 2 vectors, right? Yeah. So one vector is P1, P3. One vector is P1 and P2. Okay. As you learned in linear algebra course or other courses, given the coordinates, what will be the vector P1, P3? So basically, it'll be the coordinate P3 subtract the coordinates of P1, right? Okay, same thing for the other ones, right? So basically, what I'm saying is, this is known, right? Those are vectors known based on the known condition. Okay. Now, talking about equation, then basically it means we're gonna need a general variables. So this is a 3D space. So let's say we have another point P on this plane here. So we don't know where it is, but we call it x, y, z, right? Call it x, y, z. Okay? Yeah. So similarly, I can construct another vector from P1, okay, to P. Okay. So we can have P1 P vector constructed. Okay, P vector. Now this time, this guy is going to be slightly different from these two now, because these two are constant vectors here, right? But this one here, if you write it out, what was that going to be? It's x minus x1, y minus y1, and z minus z1. Okay? Yeah. So this vector has the variable x, y, z appear at here, showing up. Okay? Yeah. We want an equation. So now let's use the idea at here, what we just derived. The volume of a parallelepiped is equal to A dot B cross C. And in the previous lecture, I didn't prove this one, but I do have proof in the lecture notes, okay, so I'm skipping that. You can find a very simple proof that this A dot B cross C equal to determinant, okay, of, if you look at determinant of A, B, C. I'll double check. This is what I put it down at the end of the lecture from last week. Okay, so volume of this equal to this one equal to basically equal to the determinant of A, B, C. So what does that mean? Basically, when we write this symbol down here, this is determinant. The first row is A vector. The second row is B vector, and the third row is a C vector, right? C vector, okay? Yeah. So that's what I mean for this formula here. So okay. So I'm going to make use of this conclusion at here, okay? Yeah. So now, coming back here. How many? First, maybe come back here again. How many vectors? A, B, C, right? 3. Coming back here, how many vectors do you have? 1, 2, 3. So maybe you can consider this is your B, this is your C, and this is your A here. Is that right? Yeah. So now, what's the difference now between this case and that case? For this case here, the A is not in the same plane as B and C. So in this case, this vector is in the same plane as here because we're looking for the plane equation, right? Yeah. So then you think from here, if A happened to be in the same plane as B and C, and what would be this dot product? Or what would be the volume? 0, right? So that's easy. So basically, the parallelepiped, the volume will be 0 if A is in the same plane as B and C. And that's exactly the case at here, right? Exactly the case. So basically, what we're looking at here is if I write down according to the conclusion, what I have it here, then what we're going to have is determinant, okay, of this P1, P, okay, that's the A, okay, and P1, P2, that's the B, and P1, P3, that's C, is going to be 0, right? Going to 0, okay? Yeah. So then look at this one. Let's say which one is known, which one no known. If I want to use this one here, so basically I'm going to create this determinant, right? Yeah. The first row here is P1, P2, the component P1 what? Sorry, no, P1, P, right? The first row here is P1, P. Okay? Yeah. So what's the first row? It's x minus x1, y minus y1, z minus z1 here. That makes sense? Yeah. Second row is going to be the constant vector P1, P2. Third row is going to be the constant vector P1, P3, right? Yeah. It's not very rigorous, but that's the idea. You will put that into this format of this determinant. Make sense? Yeah. And then you calculate this determinant. So calculate determinant is 3x3 matrix. Just follow the formula to calculate determinant. Is that right? Yeah. So imagine what's going to come out, right? Just imagine what's going to. First row, there's the variable x, y, z. Second row constant. Third row constant. So in the end, what you're going to obtain from here is it's probably going to be something, x, something y, and something z, and in the end equal to 0. That makes sense, right? So basically, what you're going to come out of this determinant is going to be an equation in terms of x, y, z. That makes sense, right? Now this equation is exactly the equation describes what? Describes all the points defined by the 3 points at here. Okay? All the points on the same plane here, just defined by the 3 points. Okay? Yeah. But I guess you probably already think that, well, that looks like quite a bit of calculations here, right? And before you can end up with the right equations for this plane. Okay. So this is just the second basically approach here. Let's shorten or condense the information a little bit, right? See where we can come up with a more clean equation. At the same time, explains the whole idea that we just had finished at here. Okay. Yeah. So now this time, okay, we can still use this formula right here. Okay. So this is the formula here. If I go back one step, for this formula, according to the volume of a parallelepiped, that equal to P1P dot, okay, P1, P2 cross P1, P3, like this, right? Equal to this. So this is basically the formula from here to here. Okay, here. Okay. So now if you look carefully at this guy right here, okay, for this one here, P1, P2 cross P1, P3, so P1, P2 cross P1, P3, what does that give you? That gives you a vector, right? And the vector is perpendicular to which one? Drawing it doesn't make much sense. Perpendicular to the plane. Cross product, right? This is the cross product. So I'll let n equal to P1, P2 cross P1, P3. Okay. The nature of cross product, the result cross product is perpendicular to these two vectors here. Or in other words, it's perpendicular to the plane formed by the two vectors, right? Yeah. Okay. So let's call this as n here. Let's call this as n here. And then, Okay? Back to the same conclusion here. Because the volume is 0, so this dot product is 0, right? This dot product is 0. Okay? So P1P dot N equal to 0. So now, if I write everything out using this formula, let's see how clean this is now. P1P, we know what it is. It's a vector. It's x minus x1 and y minus y1 and z minus z1. Okay? Yeah. And the n, this is a vector you obtain from this cross product. And remember the nature. This vector is perpendicular to the plane you are looking for. Okay? So n perpendicular to the plane. And then dot this n at here equal to 0. Okay? Dot n. Also, the n at here is a known quantity because we know what the P1, P2, P3 are, right? So we can get this n at here. So basically n is a known quantity you can get. Okay? So let's say we define that n equal to a vector a, b, c. It's going to be a constant. Okay? Yeah, a, b, c. Okay. Then we plug this n into the dot product. Okay, so the next step is to use the dot product definition. The dot product definition is what? The component of this multiplied by a plus the component of this multiplied by b and plus the component of this multiplied by c, right? Yeah. So what we get is a x minus x1 plus b y minus y1 plus c z minus z1 equal to 0. Okay? So look at that. That basically is a much clean equation, okay, and it's actually more general, okay, in terms of information given in here. So this is basically, you look at this one here, what are known? A, B, C are constants. X1, Z1, X1, Y1, Z1 are constants. X, Y, Z are the variable. So you end up with an equation. This is the equation of plane. Okay, this is basically equation plane. Is that good? Yeah. Okay. So I'll give you some numbers, and we'll get the better ideas of this here. Okay? Yeah. But before we move on here, okay, let's manipulate this just slightly here and see if maybe we have a slightly different writing here. Because right now, you see, on the right side here, this is a 0, right? This is 0. So I'm going to expand all the terms out, okay? Yeah. So expand all the terms out. So what do we have? So let me call this as alternative expression, okay? Expand it out, I get ax plus by plus cz minus ax1 minus by1 plus minus cz1 equal to 0. Okay? See, the reason I'm reordering this thing here is because why? Because ax, y, b1, y, cz1, they're what? They're all constants, right? They're constants. So I'm going to call this whole bunch here, call it D. Okay? I'll call it letter D. Then I'll move the D to the other side. I get ax plus by plus cz equal to D. Okay? So this is the alternative, okay, expression as this. Okay, so both of these, okay, refer to the same thing. Okay, they all refer to plane equation planes in 3D space. However, okay, both of them has advantage or there's no disadvantage. So both. Well, it's probably out of battery. How about this one? Okay, cool. So both of them has an advantage. Basically, what you need. Okay, a few comments here. By observing this equation here, okay, by observing the equation, let's say, what is the coefficient? What is the coefficient in front of this x, y, z here? A, B, C, right? Or this one here, same thing, A, B, C, okay? And what is ABC then? Where is ABC from? From this one here, right? And what does n vector represent? N vector represents is a vector perpendicular to the plane, right? So basically, what happens right here is coefficient, okay, A, B, C. Okay, so basically the idea is all of a sudden you're giving an equation plane. The question tells this is the equation plane, maybe this guy or the previous one. Then you can immediately see, oh, the ABC represents what? ABC, coefficient ABC, okay, is the component of n perpendicular to the plane. Okay? Yeah. Or in other words, always remember, if you form your vector and use ABC, that vector is perpendicular to the plane you're looking for. Okay, so this is the plane, and this is n here, right? Perpendicular. Okay? Yeah. And if you are given a plane equation, the plane equation is in this format here, okay? It's in this format. Then you should know the geometrical meaning. What does x1, or what does this number here represent? Exactly. They represent the points, the coordinates of the points on the plane. Okay? Yeah. So, for example, if I give you a plane equation 3x minus 2 plus 4, y minus 3 plus 5, and z minus 4 equal to 0. Right? Yeah, equal to 0. Then your immediate conclusion, don't need to do anything else. Your immediate information you can extract out of this given plane equation is what? Number one, you extract, what do we get from the first information? We got a vector, and that vector is 3, 4, 5. And what's this vector? It's a vector perpendicular to what? To this plane. Okay? And the second information it can extract is you can get a point P, which is 2, 3, 4. Okay, it's on the plane. Okay, and this is perpendicular to the plane. Okay, that's the information, and very much you probably will use this information to further solve the given question here, right? Yeah. On the other hand, okay, if the question is giving you certain information and asks you to find a plane equation, so the question basically is to find a plane equation. Then if you are required to find a plane equation, then you only need two information to construct plane equation, right? What are the two information? One is you need a point on the plane. And the second is, you need what? You need a vector perpendicular to the plane. Once you find, if you can find these two information, all you need to do is put it into this format. That's the plane equation you're looking for. Okay? Yeah. So, okay, if you're trying to find a plane equation, okay, focus on number one, okay, try to find a vector perpendicular to the plane. Okay, and we'll look at the skills of getting those information. Okay, and we'll also look at try to find a point, okay, on the plane. Okay, so that's all we need. Okay, so if you're given plane equation, what's the information you can extract? If you're required to find the plane equation, how do I get these two information in here? So that's basically what the next exercise is going to be. Okay, let's look at a couple of examples that are here. So let's look at the first example. Any questions at this stage? Okay, so good? Yeah. I'll give you vector V. And the plane okay. So when you solve all of this following question here, you got to bear in mind the applications of dot product and cross product. Okay. So the question here is the V and the plane. Okay. What is the relationship? First, are they parallel? Second, are they perpendicular? Or maybe some other relationship, geometric relationship. Okay. It doesn't hurt to draw sometimes, just to illustrate the ideas or the wording inside of here, right? So when you have a plane here, okay, excuse me. What do we mean by the vector is parallel to the plane? So basically, the vector may be something like this, right? So it's not, basically, it doesn't matter how, if you draw a line, through the vector, okay, and that line will not intersect the plane. Okay, so that means this is parallel, right? And if this vector happen to have a certain angles, okay, you basically draw the line or intersect the plane, and that means they're not necessarily perpendicular. There may be certain angles here, right? Yeah. But if the vector is like this, okay, so then they're perpendicular. Okay. So this other probably refer to this condition here. Okay. The parallel perpendicular to refer to this and this. Okay. So how do we get the information in? Through what operation, basically? Yeah.
What is the third point of the vector?
Sorry, yeah. -1.
Okay.
Yeah. Okay. Good. So, as I said, before you move on to solve anything, this is what's given here, right? So the plane is given. As I said, what information can we extract out of this given equation? We can extract two things, right? But I guess at this point, maybe one thing is very obvious, which is what? N. So this is the plane, so we can extract the perpendicular vector n to the which is to the plane, right? So the n equal to, what would be the n here? Coefficient of x, y, z. So 1, 1, 3. Okay, 1, 1, 3. Is that clear? Yeah. So if you are illustrating this thing here, let's just say, okay, I'm trying to illustrate this. Here's a plane, right? And what we just find out is we find our n to the plane. Okay, so I'll just draw the n and here. Is that good? Right? Yeah. And you don't have a computer, so you cannot draw this in the actual very precise case. But you know, v is somehow just v. Draw it out, right? We don't know what's the relationship yet, right? Yeah. So what would you do next? Any idea? or basically going around here, if v is parallel to the plane, if v is parallel to the plane, what would be the relationship between the v and the n? Sorry? Somebody perpendicular, right? Somebody already answered. Dot product is 0, right? Or if v is perpendicular to the plane, then v and the n will be parallel, right? So in either case, as was suggested, the dot products seem to be a feasible operation that can give us the relationship between n and v, and then consequently give us a relationship between v and the plane. That makes sense, right? Yeah. So now let's carry out the dot product there. Okay. So what's the n dot v? Okay. Right. What's n dot v? So you have a v, you have n here. Okay. So if you do the calculation, this times this plus this times this plus this times this, it happen to be what? 0, right? 0 here. When dot product is 0, that means the two vectors are perpendicular. So n is perpendicular to v, then that means the v and the plane is parallel to each other. So n perpendicular to v, and then consequently v is parallel to the plane. Okay? That make sense? Yeah. Okay, so let's look at another example here. Okay. This one is relatively complicated. It needs a little bit examination. Okay. Yeah. Giving a point S, okay, and a plane So given S, a point, and the plane, find the shortest distance from this point S to the plane given it here. Okay, yeah. So at this stage, you know, a very helpful way is to always just to illustrate what's going on here, right? You don't have to be very precise. Here's a plane. Okay, here's a plane. And here's S point. Okay, here's S point. So now you probably, actually one of the questions you probably immediately jumped in mind is shorter distance from S to the plane. What if S is on the plane? Then there's no distance, right? Yeah. So, but then how do I know whether S is on the plane or not? So what shall we do? Exactly. So we can substitute these X, Y, Z. And then what? If the left side is the same as right side, it will be on the plane, right? Yeah. Otherwise, they are not. In this case, they are not. Okay? Yeah. But that's the way you can get rid of that doubt. But in this case, you are looking for is this S, the shortest distance. So shorter distance. So drop the S to the plane, and we're looking for this distance. Okay? Maybe I'll use a D here. Okay? Looking for the D distance. Okay? Yeah. So now basically up to this stage, actually, you have all the information. You learn everything. You know what to do, but just to find out the right direction, right? Yeah. So the right direction, as I always say, is nothing else but dot product or cross product. Okay, by making use of these things here, and then at the same time maintain a certain sense of geometries. Okay, what you are looking at here. Okay. So let's just say if think in the reverse way, you want to use the dot product, right? And as I emphasized, the dot product, what do we do? As I mentioned, a very common application of dot product is what? Is that projection, right? Projection. Okay? Yeah. So we're saying, okay, you want to know the length of projection, and then what is that? The length of projection meaning use the vector dot what? Dot the direction, right? So this is actually exactly the constitution we're looking at, right? So we're looking for this length set here. So basically, it's like maybe another vector project in this direction. That makes sense? Yeah. Okay, so that kind of maybe bring us somewhere now. So let's just say I'll use the first method is here, right? Yeah. So I'll give you a little more information here. See if you can come up with a solution now. Okay, so we're looking at direction here. Now, is the plane given? As I said, when the plane is given, before you do anything, write down the information as soon as possible based on the given equation. So what's the information we can write down? We can write down n here. So the n vector is what? 3, 2, 6. And know that this is a vector perpendicular to the plane, right? To the plane. And this vector actually happened to give us, what does it give us? We said we're trying to project something into this direction here, right? So actually, this vector represents the direction. That makes sense? Yeah. So, I guess if you want a direction now, you need the n hat. Okay? So how do I get the n hat? It's n over magnitude. Okay? Over magnitude. Okay? So, that's going to be the direction for the dot product. But dot product, you need a vector to dot the direction. That means, right? You need a vector to dot the direction. Where's the vector from then? Where can we construct a vector? So this is n here, and you have a point. You need a certain kind of vector here, right? So how can I construct a vector? See anybody? How would you be able to construct a vector? Let's say I already have a point S. What else do you need to construct a vector? You need origin. I think I've got origin maybe here, right? I need a point. Where? On the plane. Okay? I need a point on the plane. Then I can construct a vector. That's good, right? If I construct this vector, then the next thing is to do what? PS dot where? Dot the n hat. What does that give us? Direction? No, that gives us the projection, which is basically the D here, right? The D here. Okay? Yeah. So now all the points nailed down to, how can I find a P on the plane? Well, you have the plane equation here, right? You have the plane equation. How many points on the plane? How many points? Infinite. Infinite. So then, out of the infinite points, can you give me points on the plane?
0, 0, 1.
0, 0, 1. Does that make sense? Yeah, 0, 0, 1, yeah, right? Yeah. Can you give me another point then? Exactly, right? So basically, this is basically up to your creativity now. So you can come up with any point on the plane, right? But as long as it is on the plane, okay? Yeah. So P is on the plane. And where exactly is the P on the plane? That's totally up to you how you construct the point P so that it satisfies this equation here. So, as most of you suggested, we picked P 0, 0, 1. Okay, seems to be very simple points. Okay. Yeah, when you see origin, yeah, origin maybe is on the plane. Huh? Yeah, so that's possible. Okay. Actually, when origin is on the plane, what would be that situation? So let me go back to this equation of plane here. If the plane passes through the origin, D is 0, right? D is 0. Okay? Yeah. Okay, so if this is a P point, then the PS vector in my case, because my S is 1, 1, 3, and this is 0, 0, 1, so use the coordinate S, subtract the coordinate P, so we'll get 1, 1, 2, right? 1, 1, 2. Okay. Alright, so the rest works is very simple. So you use this vector, dot, this n hat. So I guess we still need to figure out n hat then, right? N hat. So just see what n hat is. N hat is 2, 3, 6, divided by the magnitude of this n vector. Magnitude is square root 9 plus 4 plus 36, like this, right? So 9 plus 4 plus 36, okay? What does that give us? That happened to give us 3 over 7, 2 over 7, 6 over 7, okay? Yeah. So then the D, okay, is this vector dot this vector, okay? And it's simple dot product. So you carry them out, you end up with 17 over 7. Was that good? Yeah. So let's look at another method here. Okay, second method here, just to expand our vision in here to a little bit different solution. Okay, yeah. But all the different methods here, all making use of the concept of vector. Okay. Okay, so I'll redraw the diagram here. I'll pick a point on the plane. Okay, I'll pick a point P on the plane. Okay, so arbitrary point P on the plane. And then I'm going to construct a vector PS. Okay, construct a vector out of the P and S. Okay. So now what we're looking for is we're looking for the shorter distance from S to the plane here. And in other words, if the P point represents is the shorter distance, giving you SP is the shorter distance here. So that means this SP must be what? Perpendicular to the plane. If this SP is perpendicular to the plane, or in other words, this PS vector, so this PS vector is going to be perpendicular to the plane, right? Yeah. And we have this n already extracted out of the plane equation. And we know the n in nature is perpendicular to the plane. So the PS, so we want to find a point P such that PS is parallel to the n here. Make sense? Yeah. So PS, right, needs to be parallel to n here, right? Such that basically, okay, P is, of course, P is on the plane first of all. Okay, we want, okay, PS parallel to n, right, such that this PS, right, is the shortest, okay, distance. Okay, so that's the logic of thinking it here. Okay, yeah. Okay, so then the next thing here is, okay, so let's write down the PS first. PS, P is x, y, z, and S is 1, 1, 3. So PS is 1 minus x, 1 minus y, and 3 minus z. Okay, and the n, okay, n here is 3 to 6, right? N is 3 to 6. Okay, so this is a PS. And this is n. Okay. The two vectors are going to be parallel. So then the idea is, if two vectors are parallel, what is the relationship between the two vectors? First of all, what is the common things between the two vectors? Two vectors parallel. What's the common? In the same direction. What's not in common? The magnitude, right? Magnitude. Okay, so in terms of mathematics, right? In terms of mathematics, yeah, you might argue is one pointing to the one direction, the other pointing to the other direction, right? Yeah, that's okay. So, but in mathematics, when two vectors are parallel to each other, okay, they are only different by what? By a scale. Okay, we don't know what a scale is. Okay, yeah, maybe it's a positive number. If it's a positive number, then they're pointing to the same direction. If it's a negative number, then pointing to a different direction. But if the k is not 1, right? If k is not 1, then they're basically different by a certain length ratio. Okay? Yeah. So now we have, based on this one here, so what do we get? We get 3k, 2k, and 6k. Okay, 6k. So this vector equal to this vector. In other words, if this vector is equal to this vector, that means the components of the two vectors must be the same as each other. Okay? So we end up with what? Three equations. 1 minus x equal to 3k. And 1 minus y equal to 2k. 3 minus z equal to 6k. Okay. If I rearrange this slightly, I get x equal to 1 minus 3k, y equal to 1 minus 2k, and z equal to 3 minus 6k. Okay? That make sense? Yeah. This is actually in the next. We don't have time to start with line equation. This is actually, you'll find out, this is actually a line equation. Okay, this is actually a line equation. We're gonna talk about next. Okay? Yeah. But there's a variable k here, right? We don't know what the k is yet. We have to find the key value. Then we can find the distance between p and the k. Okay? So that means we have to make use of some other information or given condition to find the value of k. So what else information can we make use of at here? Square root? No. Where is the point P? It's on the plane, right? What is the point P, x, y, z? So, what's the x, y, z now? X, y, z. So what can we do is, we can substitute this x, y, z in here back into the plane equation at here. Okay? Because P is on the plane, or has to be on the plane, right? Okay, so the plane equation is 3x, so 3x, 3, 2y, 3 to 6, equal to 6, right? So substitute this coordinate x, y, z into the plane equation, and you get this. So now this is one equation, y unknown k, right? So expand it carefully and solve for the k. I'll give you 30 seconds to see if you can get the right k. And in this course, I emphasize a lot on the calculation skill. Right? Calculation skill meaning like this kind of case, like a calculating determinant, calculate the integrals, right? Yeah. You know, anything to do with trigonometries, you know, yeah. So those are the calculation skills you will have to make use of. So what do we get? Okay, you get the 17 over 49 at here. Okay. So in the end, you can calculate d. That's the absolute value of the PS. Right. So now you have the point P now, coordinate. You have the S point. So you can calculate this one here, and you will end up with the same results as in method 1. Okay. Was that clear? Yeah. So the way to solve any of this kind of problem, particularly seeming to be not so easy question, is to establish a logic way of thinking, right? Yeah. Okay. So, you know, I'll skip one example here, but maybe not. Let's just quickly show you what this is. So if you have two planes given, okay, then my question is, what's the angle between the two planes? Okay, find the angle between these two planes. Right? So geometry, you know, here are two planes. What's the angle? Angle basically means the two planes must intersect each other, right? Yeah. So you can definitely think, well, maybe the two planes are parallel to each other. If they're parallel to each other, then there's no angle, 0, between the two planes. So the quick question to ask is, here are the two planes. How do I know whether the two planes are not parallel or parallel? Pardon me?
Dot products of perpendicular lines.
Dot products of the perpendicular line. That's right. So you're thinking in the right direction, absolutely. And basically, if there are two planes that are here, right? Yeah. And you're looking for the angle between the two planes. Okay? Yeah. So what we can do is we can, okay, even before you do anything, you can construct the two parallel lines, two parallel vectors out of the two equations given. Okay? And the angle, or whether the two planes are parallel or not, can be determined by dot product of these two vectors. Okay? And as a matter of fact, the angle between the two planes can be depicted by what? The angle between the two vectors. Right? Yeah. So if you remember, when you the dot product, there is a formula which is what? Right? Which is this. Okay, which is this. So that's basically the alternative approach, finding the angle between two planes. Okay, yeah, based on the two normal vectors. Okay. Okay. Yeah. So you can try to calculate this one here. Okay. It's pretty straightforward. Okay. Okay. So to summarize here, you just bear in mind when you do assignments, you probably will see some kind of questions arising from what I'm going to summarize it here. Okay. Yeah. The kind of questions that are related to planes, probably like what we did, find the distance from a point to a plane. Okay, from the distance from point to plane. And like the one we just did, angle, okay, between two planes. Okay. And the other type of equation that you will see in assignments is to ask you to find plane equation based on certain given condition. Find plane equation. Okay. So once we finish the line equation, we'll have a few more questions finding equation of planes. So for this particular type of question, finding plane equation, what you can have is, let me list down the given information. Given a point and a normal vector. Okay. So you have a point, you have a normal vector. What is the plane equation? That's the simplest. That's basically you can't have any simpler question now, right? Yeah. Just plug it into the plane equation. You have the plane. Okay? Yeah. So A, B, C, X naught, Y naught, Z naught, right? That's the plane equation. You're given a point, okay, and what we call is another parallel plane. Okay, so here's a point on that plane. Here's another plane which is parallel to the one you're looking for. Then what is the plane for that we're looking for here, right? So think about this. Given 3 points, what is the plane passing the 3 points? Given a point and a line, okay, to which the plane is perpendicular. Okay, so you have a point on the plane goes through one point. At the same time, the plane is perpendicular to a given line, right? And then what will be the plane equation? So that question will be able to be answered after we learn the line equation. Okay? So another one is you're given a point here, okay, and the line. Okay, the plane goes through. So the plane goes through a given point and a given line. And how do we find the plane equation? Okay, so that's another type of question. Okay, yeah. So assuming the point is not on that line. Okay, so here's a point, here's a line, and what will be the plane? Okay, determined by this point and the line. So that's sort of the kind of questions you probably will. Actually, I think that's all the possibilities that you will be able to see based on the plane kind of equation. All right? Yeah. So bear this in mind as to these possibilities. All right. Any questions? So we're not done yet. So I still have how many? Still have 5 minutes. So I want to start the line equation. All right? Yeah. Are we all good? Okay, good. Okay. Equation of lines. Okay, so 3D space, x, y, z, and here's a line. So we want to know how do I describe this line equation. All right, that's the purpose. Okay. Now, if I think back on the plane, okay, so what gives us a line? When two planes, what? When two planes intersect each other, you get what? Okay. Pardon me, my drawing. When two planes intersect each other, you get a line, right? You get a line. Okay? So the simplest solution, okay? As a matter of fact, this is doable, okay? You want this line? You give him two planes. So you give him, here's one plane, another plane. The intersection gives you the line you're looking for. Okay? But of course, right? Okay, so given two intersected plane, okay, we have a line, right? We have a line. But this is definitely not so clear because not like a plane equation. Look at the plane equation, right? And ax plus by plus cz equal to d. You plug x, y, z. That's a plane equation, right? But you give me two planes. What line are we looking at? It's not clear. Okay? Yeah. So we need a little alternative approach at it here. Okay? So the alternative approach at it here is actually this concept we're going to make use of similarly is this. So let's say I have point x, y, z at here. Okay, x, y, z. And now, okay, assuming that this point x, y, z, okay, is going to move along this line. Okay, it's going to move along the line. So at this time instant it's here. At the next time instant, maybe it's here, or maybe it's here, right? So then, for this particular point P, which is representing position, each one of the coordinates x, y, z here is going to be a function of what? Because it's moving, right? It's moving. So at this point it's here, at that point here, at each point x, y, z is going to be different. Then the point P can be characterized each one of the components can be characterized as a function of what? The time t, right? Okay, time t here. So the idea is, okay, we're not gonna like a plan equation. You know, all the x, y, z appears in one expression. Okay, and here we're going to focus on individual x, y, z. Each one of x, y, z is going to be a function of t, or maybe something else. Okay, or s or u, doesn't matter, a variable. Okay, but the idea is we want to come up with an expression for each one of this. So we're going to have an expression 1, and expression 2, and expression 3. Of course, all the expressions here are going to be a function of the t. Okay? So, given a different t value, you will have a different x, y, z value. Right? That's basically the idea. So, this is the idea. So, get 3 expressions all in terms of t. So then, in terms of the mathematics, this is called, we're trying to obtain a so-called parametric equation. Parametric equation. So that's a new one concept. So you're going to have 3 equations, all in terms of parameter t. So that's called parametric equation. Okay? Yeah. Now, what does that parametric equation describe? It's going to describe, as we want it, it's going to describe the motion of the p on the line L that you're looking for. Right? Yeah, so that's the point here. So to get, it's a little bit tight here. You know what, let's start from the next lecture. Yeah, so, okay? Yeah, fresh start. Any questions? Okay, okay.